Good morning, I'm Mr. Precella, and I'm going to continue my discussion on limits and continuity for my Math 1325 class. This is a big unit right here, so yeah, we've been going at it for 2 videos. Now we're going on. Let's continue on, and I think we'll go back to number 15 and work this problem here. I say work, really there's no work to it. You're just analyzing the graph. So remember the notation that they had. They want us to find the limit as x approaches -4 from the left, the limit as x approaches 0 from the right, the limit as x approaches 2 from the left and 2 for the right for the function f of x. And that's because I have trouble seeing those little signs in the superscripts. Notice I've rewritten the problems right here, the 4 problems. So start off, we're looking to the left. That little superscript says you're looking to the left of -4 on the x-axis. 1, 2, 3. So there's -4. We're looking to the immediate left, right out there. To the immediate left of -4. Reflect that up onto the graph. As you move this way for x, on the x-axis, the graph is moving, getting closer to that open circle right there. All of those y coordinates right there are approximately equal to whatever this y value is. What is that? 1, 2, 3. So the limit as x approaches -4 from the left is 3. What about the limit as x approaches 0 from the right? Here's 0 on the x-axis. We're looking to the immediate right, right out there. Maybe hard for you to see that portion of the graph. All those y coordinates are real close to what? Looks like it's getting closer and closer to the origin. Those y coordinates are close to that portion of the graph. I agree with the 0. So that's saying that to the right of 0, the ordered pairs on the graph, they're close to the origin, 0, 0. What about the limit as x approaches 2? There's that little superscript minus. What side is that? Is that, here's 2. Are we looking to the right or to the left? We're looking to the left. Okay, so we're looking right, and we're looking here to the left of 2. These y values are going up and up and up. Are they approaching a single number? No, they're not approaching a single number. This thing does not exist. If I wanted to make a general statement about the what's happening, though, I think we can describe what's happening. What's happening to the y values out here to the left of 2? Look at this portion of the graph. They're getting bigger and bigger. And so I would say those y values are increasing without bound. When x is to the immediate left of 2, the y values are getting bigger and bigger. So I would use an infinity because that's more descriptive than just saying does not exist. What about the limit as x approaches 2 from the right? Here we're to the right of 2. Look at what's happening to the graph. It's continuing on down. What could we say is happening there? Those y values are doing what? Those y values are getting smaller and smaller. So here, I would say negative infinity. So here I'd have a 3. This one I'd have a 0. This one, even though the limit doesn't exist, we can describe what's happening. It's going to infinity. And to the right of 2, right here, it's going to negative infinity. Let's see about another one. Let me move this and shuffle through my papers to see if I can find another one. Ah, here's something. Use the graph of the function f to find the following limit. That says the limit of f of x. Look, it's not x arrow a number. It's x arrow infinity and x arrow negative infinity. They have 2 limits they want us to find. The limit x arrow positive infinity and the limit x0 negative infinity. What do you think that means? We're not looking at what's happening as x gets close to a single number. We're looking, where's x0 infinity? The x-axis, as it's getting bigger and bigger, that's on the extreme right-hand side. So x increasing without bound, you're looking on the extreme right-hand side. What's happening to the y coordinates on the extreme right-hand side? This one here, x0 negative infinity, x is decreasing without bound. X is going, you're looking at the x-axis, that's extremely negative, way out here. What's happening to the y values? Let's do x increasing without bound. Way out here, x goes to 5, 10, 50 million. It's going further and further out at a positive 50 billion. What's happening to those y coordinates? The graph is going down more and more, so I think I can be descriptive. How can I describe what's happening to those y coordinates? As x gets bigger and bigger, the y values are getting more and more negative. Yes, negative infinity. That's how I would write it. What about here on the left-hand side of the graph? These limits as x increases or decreases without bound, it tells you nothing about here in the middle of the graph. Only what's happening on the far right or on the far left. Okay, x is getting more and more negative. They're trying to show a horizontal asymptote there. They're showing a horizontal asymptote. As x goes, as we look further and further to the left on the x-axis, the curve is approximating that horizontal asymptote. Well, what is that horizontal asymptote? What number does it pass through on the y-axis? That's negative 5, 4, 3, 2, a negative 1 for my final answer. Take a moment and look at that. Any questions there? x0 infinity, that's saying what's happening way out here to the right. x0 negative infinity, what's happening way out on the left. Here on the right, the y values are getting more and more negative. What's happening on the left? On the left, the y values, they're getting closer and closer to that horizontal asymptote of negative 1. Here's another one, number 18. It's another situation where we want the limit as x decreases without bound and the limit as x increases without bound. I'm going to write it out right here. The limit x0 negative infinity of f of x. Oh, by the way, up here, that would have been, here we would have written in the negative infinity, or typed it in, and here we would have typed in the negative 1. Here they want the limit as x decreases without bound, and the limit as x increases without bound. So, first of all, x0 negative infinity. What side of the graph are we looking at? The right side or the left side? The x-axis where it's extremely negative, that's the left side. All of these y coordinates way out here are approximately equal to what number? 2. I agree. So x0 negative infinity is 2. What about x0 positive infinity? X is increasing without bound. As x gets bigger and bigger out here, all of those y coordinates, once again, they're close to what? Close to 2? I agree. These two problems that I've just done are limits as x increases or decreases without bound. Instead of x approaching a number a like those examples we saw in the two previous videos, here x is getting bigger and bigger and x is getting smaller and smaller. What's happening on the extreme right? What's happening on the extreme left side of the graph? And let's see what else we have. Continuity. Continuity. A continuous function. A continuous function is one that has, I'll say, I don't really need to number it, I'll just say there are no holes, no jumps, no vertical asymptotes, just from having been alive, as long as we've been alive, we have an idea of what the word continuous means. So, and that's exactly what we think algebraically. The graph is no holes, no jumps. It could do something like that and go on like that, but you're not going to pick up your pencil and move from one side of a vertical asymptote to another. You're not going to have any little holes. You're not going to have jumps where the graph stops and then jumps up or down. So with that in mind, let's look at number 19. Oh, another term. If a function is not continuous, we say that the function is discontinuous. So discontinuous means the function is not continuous there. That means if it's not continuous, that means that there's a hole or a jump or a vertical asymptote, okay? I'll say graph has hole, one of those missing points, jump, or vertical asymptote. So looking at this is my number 19 that I printed out. Find all points of discontinuity for the function whose graph is shown. I see two different places in which I have a point of discontinuity. And even though it's not really an ordered pair, this is one of the few times when we refer to points when there's not necessarily an ordered pair. For example, I see a vertical asymptote right there. We have a vertical asymptote at -3. We have a vertical asymptote at -3. And we have a missing point, one of those holes. I see right here we have a hole, I'll call it a hole, when x is -2. So there are two places in which there's a point of discontinuity. We have points of discontinuity at -3 and one at -2. Don't make this more difficult than it is, okay? So it's exactly what you would expect from the word continuous. Look at the next one. Let's see, this is number 20. Let me move it up a little more. Find all points of discontinuity whose graph is shown below. Anywhere we have a point or a missing point or a vertical asymptote or a jump, we have a discontinuity. I see 2 points of discontinuity. They may be hard for you to see on the screen, but at -4, I see a missing point right there. That's a little open circle. Can y'all tell that? There's an open circle on that graph. So we have a discontinuity there at -4. Also, we have another open circle here at +1. Can y'all see that? Both of those are holes. You have a missing point in both situations. It's a missing point. And we could actually, discontinuities of this type are frequently referred to as removable discontinuities because we could remove it. If we could change the function, you see that little dot there? We could pick that dot up, move it down, fill in the hole. Pick that dot up, move it down, fill in the hole. Do y'all see any other points of discontinuity? You see another one? Yes, right here. There's another little missing point. And what's that x value? It's another discontinuity. That little open circle there. There it is at, so we said it was at We had a discontinuity at -3. We had a discontinuity when x equaled 1. And finally, we have a discontinuity right here when x is equal to 3. So there are 3 places on this graph at which we have discontinuities. -4, 1, and 3. That looks like response B. And let's see if I can find another one. Oh, here's a good one. So find all values x equals a where the function is discontinuous. Look at that graph, and I can see a jump. There's a jump, so there's definitely a discontinuity, but I think we have a missing point also. We have a missing point that's occurring. Right here, we have a jump. We also have a missing point. So, but you're drawing the graph on, and then you have to jump up. So what is that x value there? It looks like they're incrementing in units of 10. This is terrible. I need to get out my magnifying glass. 1, 2, 3. So it looks like there's 1 when x is equal to 3. And there's 1 more when x equals what? Right here. When x is 0, we have that little open circle there. Notice they have the little closed dot way up there. But right here, at x equals 0, we have a discontinuity. So there are 2 points of discontinuity, at 0 and at 3. For my final answer. Take a moment and look at that. Get up real close to the screen to see it, I guess, because unfortunately, that's as close as I can get it there. And there can't be, surely we'll need to determine when a function's continuous when we're without looking at a graph. Well, we've already sort of mentioned that when we were looking at polynomial and rational functions. We said a polynomial function's limit is always defined. It's a continuous curve. There's no holes or jumps or, let's see, for a polynomial function, it's always continuous. There's no holes, no jumps, no vertical asymptotes. U-O-U-S there, okay? Polynomials, always continuous. Rational functions, that's when we have to worry about. Those are the ones that have the missing points and the vertical asymptotes. Remember I said that you have a hole if the value of the denominator is 0 and the value of the numerator is also 0. You have a vertical asymptote in a non-zero over 0 situation. But the key is for rational functions, they're continuous as long as they're defined. Well, a fraction's defined as long as its denominator isn't 0. So a rational function is continuous. Okay, as long as its denominator is not equal to 0. Remember we said if we have a 0 over 0 case, 0 over 0, that's one of those holes or missing points. If it's a non-zero over 0, not 0 over 0, that's when you have a vertical asymptote. So looking here at number 22. Is the function continuous at the given values of x? The function is continuous as long as that denominator isn't 0. So when I look here, I can tell there are 2 values where it's not going to be continuous. When is that denominator equal to 0? Well, that denominator is equal to 0 at 0. and at negative 3. If you plug in negative 3, you get a denominator of 0. If you plug in 0, you get a denominator of 0. So is the function continuous at x equals negative 3? No, because you have a denominator of 0. Is it continuous at x equals 0? Plug in 0 down there in that denominator, what are you getting? You're getting 0, so no, it's not continuous there. Now 8, plug in 8. That's an 8 times 8 plus 3 is 11. Do you get a denominator of 0? No, that denominator does not equal to 0, so yes, the function is continuous at x equals 8. It's continuous as long as its denominator is not equal to 0. This thing here, when you plugged in 8, the denominator wasn't 0, so the function's continuous. Let's do another one. Okay. Determine if the function x plus 6 over x squared minus 13x plus 42 is continuous at 0, 6, and 7. Okay, let's start with 0. Where do you plug in 0 to decide whether it's continuous or not? You plug it into the denominator. Plug in 0 into the denominator, you're going to have a 0 minus 0 plus 42. Is that denominator equal to 0 then? No, it's not 0, so yes, the function is continuous there. What about 6? Plug in 6. Plug 6 into the denominator. 6 squared is 36 minus 13 times 6, is that 78? Yes, it is. Plus 42. Is that denominator 0? Yes, that denominator is 0. That denominator, I'm going to make a note, the denominator is equal to 0, so no, the function's not continuous there. What about when you plug in 7? When you plug in 7, what are you going to get? What's the denominator going to be? 7 squared is 49 minus 13 times 7, that's a 91, and we still have that plus 42. What's that denominator reducing to? Yes, it's given us another denominator of 0. So is the function continuous there? No, we either have a whole or a vertical asymptote, but it's not continuous. Suppose I wanted to decide, does the graph have a whole or does the graph have a vertical asymptote? I'd have to take that 7 and plug it into the numerator. That would be 13, non-zero over 0. Non-zero over 0, that's a vertical asymptote. And any questions there? A rational function is continuous over its domain. If you remember how we found domains of rational functions in previous math classes, we said a fraction's undefined whenever the denominator is 0, so we find when the denominator is 0 and discard those. The denominator's 0 at 6 and 7, we discard those. The function's not continuous. At 0, the denominator's not 0, so yes, the function's continuous. What about number 24? Oh, this is nice. What sort of a function is this? We discussed this in the previous video, I think. That's a polynomial function. Polynomial functions are always continuous. That's a polynomial. Notice there's the exponents are non-negative integers, an x squared and an x to the first. You have no variables in denominators, no variables under radicals, so this thing is a polynomial function. And polynomials are always continuous. So down here, I would choose B. The function of f is continuous for all values of x. What about this one? It's a fraction. When would that function be discontinuous? I'm not going to say anything. You think of that answer. I'll tell you right now, there's a time when it's not continuous. When is it discontinuous? It's discontinuous when the denominator is equal to 0. Is it discontinuous when the denominator is equal to 0? So what value of x gives us a denominator of 0? It should be obvious. When x is 3. So right here, I'd type in 3. And I've given y'all a lot to think about here in this first homework module on limits and continuity, and hopefully these examples will help you get through some of the homework. So hopefully it'll help you get through all of the homework. But anyway, then I am Mr. Precella, and I'm going to take a break, and I'll let y'all work on the homework for a while. Okay, bye bye.